marvelous. That's why I've got two fill lines up there. Okay, so let's talk about the maximum principle. Okay, so I don't know, have we talked about strict partial orders before? Anyway, it's we've talked about simple orders, haven't we? Okay, so a strict partial order just means we have the strict comes from non-reflexivity, which means that A can't be less than A. Transitivity holds, and you go from a strict partial order to a partial order if you allow equality. So whereas the less than is a strict partial order, less than or equal to is a partial order, because either A is less than B or A is equal to B. So it's weaker than the definition of a simple order. Remember, in a simple order, you also have to have comparability. So that if A doesn't equal B, you have to have A less than B or B less than A. So that's where the partial comes from. Partial because only some of the elements are comparable. Okay. But if you think about it, if you've got a set and it's got a partial order on it, then it's possible for some subset to be a simple order, but i.e. in some subset, all the elements in that subset are comparable to each other. Okay, every pair of elements is comparable. So an example is in the plane, and we can say that AB is less than CD if B equals D and A is less than C. Okay, so this is a partial order. And points are comparable only if they lie in the same horizontal line. So if they are in non-horizontal, if the x coordinate, the y coordinate is different, they lie in different horizontal lines and they're not comparable at all. And these horizontal lines are maximal. Right, so if you added, so here we go, here is our horizontal line. Every element in that line is comparable to another, and if we were to add another point to this subset, then it would no longer be a simple order because we couldn't compare this point to any. So this is the whole thing with, so we're going to be looking at sets which has a partial order on it, and we're going to be looking at maximal simply ordered subsets. Another word people use for a simply ordered subset is a chain. So it's a chain because everything is, put it all into that order. Okay. So the maximum principle that we're talking about. So this goes back to Hausdorff, 1914. Let A be a set. Let's say we have a strict partial order on our set. Then there exists a maximal simply ordered subset B of A. Just saying that such a thing exists. Another way that some people talk about that is it's saying that every simply ordered subset of A is contained in a maximal simply ordered subset. And it's easy to see that that is equivalent, right? let's see. Let's go from here to here. The empty set is trivially simply ordered. And so by this principle here, it's contained in a maximal simply ordered subset. And so that's Hausdorff's original thing. Whereas, say, this is true. Why is it true that every simply ordered subset is contained in a maximal simply ordered subset? At first glance, that might not be obvious, but if you considered, say you're given a simply ordered subset of A, and you want to show that it's contained within a maximal one, then just yeah, I think I've screwed things up by leaving my Zoom on in my office. But anyway, where was I? Okay. So if you consider this this set, it's also a partially ordered set by set inclusion. Therefore, by the maximum principle, it has a maximal simply ordered subset D of the power set of A. And then if we just let D, capital D, be the underlying set that the power set is, then that is a maximal simply ordered subset that contains C. So that is the maximum principle. And so let's naively try to prove that. And we'll soon see where we need our friends, acting the choice, the order to do that. So let's just simply try and define a maximally simply ordered subset by, okay, we start off with an arbitrary element of A. That's going to be, we're going to throw that into B. We pick another element. If it is comparable to the first element, put it in B, otherwise put it in A minus B. I'm putting quotation marks here because I've got problems because I haven't defined B yet. So it's like I'm making a box and I'm putting things in a B box and an A. So really what we want to do is we want to index, we want to set up a set of B's that indexed by some set that eventually is going to lead to B. And so then at the general step, we have a collection of elements that we've chosen to be in B and a collection of elements that we've chosen to be in A minus B. And we take one of the elements we haven't considered yet. And if it's comparable with everything in what we want B to be, we put it in B. Otherwise, we put it in what we want to consider A minus B. And after we have checked all the elements in A, the elements in what we thought of as B is our actual B. And it is simply ordered because everything we put in there was comparable to each other. And it's maximal because there was nothing that we could put in from A minus B that we put in that would be comparable to everything in B. So that's a rough idea of how the proof goes. this is what Hausdorff did, and it seems kind of obvious. But of course, the problem is, what do we mean by after we've checked all the elements in A? Okay, well, there's no problem if A is countable, right? Because then if A is countable, then we've got an order in which we can go through A and check every element to see whether it's in D or not. And we can use that principle of recursive definition that we talked about at the start, where we can define a function from Z plus, right, which is our index set, to 0, 1. And we define this recursively, right, where HI equals 0 if AI is comparable to every element of the set AJ, J less than I, and HJ equals 0, i.e. that's what we mean that we put it in the set B, and HI equals 1 otherwise, i.e. we put it into A minus B. So this just rigorously allows us to do what we did naively before. Okay. But that's if A is countable. What happens if A is not countable? Then we're going to have to use well ordering. So then what we do then, we index A by some well-ordered set J, and we use the general principle of recursive definition, which I think I put as a homework problem, and we can define a function that goes from J to 0, 1, and the proof then just follows straight away, because we have this theorem which says if we've got a well-ordered set, C any set, and we'll let F be the set of all functions, nothing sections of J into C. Given a function rho from F to C, there exists a unique function H J to C such that H alpha is rho H restricted to that section. And so that allows us to do recursive definition over uncountable sets. So that's, but straight away we can see that we need the well-ordering theorem implies the maximal principle. And we know, right, that well-ordering is equivalent to axiom of choice. So this all came to a head like in the late 18th century and early late 19th century and early 20th century, all these kind of things. So here's another example of a maximal simply ordered set. So the standard relation that we use in all these problems is a proper subset of, and that makes quite a good strict partial order. So if we let A be the collection of all circular regions in the plane, then these are examples of maximally simply ordered subcollections. Right, so we have a collection of all circles centered at a point. That's going to be a maximal. Or if we have a collection of circles all tangent to a given point, that will also give another maximal simply ordered subcollection. Okay, so let's do a little bit of set theory or logic. So, as I said, we need well-ordering theorem to prove the maximum principle. And in fact, all these are equivalent. So I think Cantor was the first person come up with the idea of a well-ordering theorem, and he just proved it, said it because he said it was obvious. Zermelo in 1904 tried to prove the well-ordering theorem, because I think someone beforehand had said that they proved that R couldn't be well-ordered, but Hausdorff showed that the proof was nonsense. So Zermelo said, okay, I'm going to prove the well-ordering theorem. And he came up with the axiom of choice to prove the well-ordering theorem. And as I said, Hausdorff came along in 1940. So all three are really equivalent. And it turns out that there's lots of others that. So Kuratowski in 1922, he was part of the Warsaw School of Mathematics, including people like Barnard and Tarski, that kind of school. He came up with something, so you've got a collection of sets. Suppose every sub-collection that is simply ordered by proper inclusion, the union of the elements of B belong to A, that A has an element that is properly contained in no other element of A. That's really just another way of saying Zorn's lemma, which says that a set that is strictly partial order, if every simply ordered subset of A has an upper bound in A, then A has a maximal element. That's the one you've probably heard of for proving that the vector space has a basis. And then there's Tukey's lemma in 1940. If you've got a collection of sets, if A is of finite type, which I'll still say what that is in a moment, then A has an element that is properly contained in no other element of A. And so these three are really the same thing, just stated in different ways. So for Zorn's lemma, an upper bound, right? So you've got a strict partial element. An upper bound on B is an element of A, doesn't have to be in B, such that for every B in B, either B equals C or B is less than C. And a maximum element is an element of M of A, such that for no element does relate is M less than some other element. And in Tukey's lemma, finite type, what that means is if you have a collection of subsets, the collection is of finite type if such that if you have a subset B in that collection, every finite subset of B has to be in that collection too. So we're not going to go into all the implications, but let's just go through a few. Why does the maximal principle give us Zorn's lemma? So we can prove Zorn's lemma using the maximal. Prove that, well, suppose we have a maximal simply ordered subset B of A. Well, Zorn's lemma, the hypothesis of Zorn's lemma says that B has to have an upper bound C in A. Well, this C has to be a maximal element, because otherwise B union C would be simply ordered, right? Because if C is bigger than everything in B, we can add C to B and still keep it simply ordered, and that contradicts the maximality of B. It's a maximal principle gives us Zorn's lemma pretty straightforwardly. Zorn's lemma gives us Kuratowski's lemma also very straightforwardly. So let's say you have some collection of A that's simply ordered by proper inclusion, and the union of the elements of that sub-collection belong to our A. Okay? Well, this union of the elements is an upper bound for that sub-collection. Zorn's lemma says there's a maximal element, and so that means there is a set in A such that no other set in A contains it. And then for homework, I'm going to get you to show that Kuratowski's lemma implies Tukey's lemma, and that Tukey's lemma implies the maximum principle, and you've done a full circle then, showing that those four things are all equivalent. And we know that they're all equivalent also to the axiom of choice and the well ordering, but we won't go into that. That would be in a logic class, we could do that quite straightforwardly. Okay, but Zorn's lemma is pretty good, right? Because if we look at Zorn's lemma again, it's saying that A has a maximal element. And that's what's useful about Zorn's lemma. So if you want to prove, you want to prove the existence of some mathematical object, and you've got to be able to view it as some maximal object in some partially ordered set. And then typically you then prove it by contradiction. You assume that there's no maximal element, and then use whatever situation you have to get a contradiction. So Zorn's lemma is kind of useful. So here's some examples. So you've already seen that every vector space has a basis. There's a Hahn-Banach theorem, which is like an important theorem in functional analysis that says so a linear functional. A linear functional is basically just a function on function. So, for example, the evaluation is an example of a linear function. And it shows that you can extend it if you've been able to define it on a subspace, then you can extend it to the whole vector space. Another kind of maximality thing. But every non-trivial ring with unity has a maximal ideal. And in logic, that every proper filter can be extended to an alter filter. It's abstract nonsense, which allows you to do, like it's used in Gödel's completeness theorem, for example. A filter is just a type of ordered set, and an alter filter is a type of maximal partially ordered set. It's definitely in Zorn's lemma. Reach, and next class we're going to use it to prove Decomp's theorem that that in the product topology the arbitrary product of compact spaces is compact. So this is what we would have done in which class was that in? Would that be in linear algebra? Okay. Want to prove that every space has a basis. So say you're given some sort of set of independent vectors, and you've got a vector that doesn't lie in the span of A, then if we add V to A, we're going to get a set of independent vectors, right? Because otherwise, if they were dependent, we would have some non-trivial linear combination equal to the zero vector. Right, we'd have 0 equals C1 times B. Let's do the A's first. A1 plus Cn AN plus C times B equals 0. So if C was not equal to 0, then that would tell us that A wasn't linearly independent. And if C is non-zero, then we can write B is a linear combination of the A's, and so it wouldn't be the span of A. So now we use Zorn's lemma. Oh, we're going to use Tukey's lemma. We'll do it both ways. Let A be a collection of all the independent sets partially ordered by proper inclusion. Then B, then some set of independent vectors is going to be in A if and only if any non-trivial linear combination of any finite number of vectors of B is not a zero vector. And that means if and only if any finite subset of B is in A. So therefore, this collection is of finite type. Tukey's lemma applies, and A has a maximal element. And that X maximal element found is a basis. Independent. And there cannot be a vector not in its span, as that would violate maximality, right? Because if it's not in the span, that means you could add another vector to that. If you perfectly alternatively, you just want to use Zorn's lemma, you take a simply ordered subset, some simply ordered subset of B, the union of all the independent sets in B, right? Because what is B? B is like a collection of a chain of independent vectors, one contained within the other. Take the union of all the independent sets in B, that's an upper bound for B, and it's independent. Hence, by Zorn's lemma, there's a maximal element. And then go back to this thing. So that's probably how you probably did it this way when you did it in linear algebra. I think
we only did the finite dimensional cases, the actual group, and like use this thing called Zorn's lemma.
Oh, okay. Okay. Yeah, okay. So, yeah, you don't do much infinite dimensional vector spaces in undergraduate linear algebra.
You know, a little bit, but certainly we talk about bases.
And finally, let's show that every non-trivial ring with a unity has a maximal ideal.
What's an ideal here? It's like a module kind of, isn't it?
Okay. Oh. So if R is a ring, an ideal is an additive. So ideal is kind of like for rings what normal subgroups are for groups. So it's an additive subgroup, and R times I is contained within I, and R is contained within I for R in R. So multiplicity, it's going to be from the whole ring. So for example, if we look at Z, 2Z is an ideal, right? Because you take You take add any two even numbers, you get an even number. The inverse of an even number is an even number. 0 is an even number. But then if you take any element of the ring, 3, and you multiply it by an even number, you get an even number.
Yeah, but an ideal is an R module, isn't it?
Yes. Yeah.
Yeah, that's where I'm. Okay.
Yep.
But
Yes, because you can multiply things by R. So that's makes
it all
it.
stays inside the module, and you just get the module properties from the ring properties.
Yeah. Exactly. And the thing that you notice then, and if you did this in, if you look at Z mod 2Z, you get Z2. So if you take a ring and you factor out, you look at the factoring by a maximal ideal, you always get a field. Or is that a prime ideal? I think it's a field. Right, because it's a maximal ideal, can't get 0 divisors, something like that. Anyway, that's what an ideal is. So now we're going to so this is a little bit more subtle than the one that we did before, because a maximal ideal can't be the whole ring itself. So a maximal ideal by definition is a proper ideal. Right, because R, of course, is itself an ideal of itself. But so if we look at the collection, that should be collection of it. Say, let P be the collection of all ideals in R except R itself, ordered by set inclusion. And let's say we have if we start off with a simply ordered subset of in our collection, then let's look at the union of all the ideals in our chain. Firstly, why is I non-empty?
I mean,
What has to be in every?
there has to be a simple subset.
Right, but why does there have to be something in that subset? Because the empty set, right, is trivially simply ordered.
Right.
So we've got to prove first something that is something in I.
Oh,
So R can't. So the trivial ring is just 0, right? So that means P has to contain 0.
okay.
So 0 has to be an element of P. So 0 is in I. Secondly, I is an ideal. Okay, so what have we got to show? We've got to show that it's additive subgroup. So if we've got 2 elements of I, then they must be elements. There must be elements in something in the chain. One has to be in some, I don't know, I alpha, another has to be in some I beta, but one of them has to be further along. So that means they have to, so if beta is further along than alpha, then both elements have to be in I beta. So since that's an additive subgroup there, the addition has to be in I beta, so therefore it has to be in I. The second thing we have to check is multiplication by R. Well, again, if we take an element of I, it has to lie in some ideal. So if we multiply by R, it has to remain in that ideal. So I is an ideal. Here's the thing where it's different from before. I cannot be all of R, right? Because we're looking at all ideals in R except R itself. Why is it not all of R? Because sometimes when you take the union of some expanding thing, you end up with the whole space. Why is not? So we haven't used the fact that it's a ring with unity yet.
So what are we saying? The one is not in that.
Exactly, right? Because if 1 is in the ideal, then the ideal equals R, right? Because of this property here. If we have 1 here, R times 1 has to lie in the ideal. If R is an arbitrary element of R, then I has to equal R in that case. Okay, so we have to show that 1 is not in I. Well, what would it mean for 1 to be in I? If 1 is in I, that means 1 has to be in some ideal in that chain. But that chain is specifically ideals not including R. So none of those ideals is 1 an element. So 1 can't be an element in the final union. Okay. Hence, that's an upper bound. And so we use the Warn's lemma and say that it has a maximal ideal. Okay, so just to illustrate why unity was important, consider this ring here. So Q with normal addition and trivial multiplication. By trivial multiplication, I mean that R times Q equals 0. Every multiplication is 0. Okay, so what's a maximal ideal? Maximal ideals are the same thing as additive subgroups of Q. Does Q have a maximal additive subgroup?
Now it doesn't have a 1, right?
Right. So it has 1, but it's not 1 is not unity. It doesn't have it yet. It doesn't have a multiplicative identity, even though it has a 1. So I don't know.
We can't use that here. So I think the answer is no.
No. Okay. Now think about it. So you've done some module theorem. So have you done a thing about finitely generated Z modules?
I read it. I read the proof. That was a while ago.
Right. Well, the thing is, think of Q as a Z module. It's not finitely generated. Right, because you have 1/2, you can see generated by 1/2, 1/4, 1/8, 1/16, etc. So it can't have a maximal subgroup, right? Because if it had a maximal subgroup, you would have like a minimum element, some 1 on n, but then you look at the thing generated by 1 on 2n, and you get something bigger. So you can't get anything maximal. So when you try and do this thing of taking a chain and taking the union, there's no way of it stopping, and you'll end up with you'll end up with by as long as a Q can be will be the upper bound, and so you haven't found yourself a maximal ideal. So you needed the unity to make sure of this step here. So I thought that was a little bit interesting.